Okay, lesson 2.2 is power functions. And as we talk about power functions, one of the big things I want to remind you is we talked about in lesson 2.1 polynomial functions. Do you guys remember anything about polynomials? Like how we were able to tell if something was a polynomial or not? And the key is really about the exponents. Because, it's terms add or subtract together, but our exponents for a polynomial had to be what kind of numbers? Whole numbers, right? So positive, non-fraction, non-decimal. Okay, so that's in general polynomials. Polynomials were adding terms together. So our big talk today is power functions. You'll notice at the bottom we're going to talk about something with monomial. We'll talk about that in a little bit, but power functions. So with a power function of the form f of x equals k times x to the a is our power function. Can you guys read that? The fact that maybe it's just me, but that says k times x to the a, and that is a power function. Our restrictions here, very important to notice, k and a are non-zero constants. Non-zero constants means they can be anything but 0. So if k is 0 or a is 0, it's not a power function. Otherwise, it's a power function. So basically, x to any power except 0 falls into the definition of a power function. Notice a is considered the power, of course, and k is the constant of variation, which should sound a little familiar to some other topics we had in Algebra 2. Constant of variation or proportion. Also in terms of wording, f of x, or we often think instead of f of x, we sometimes think of that as y, right? Varies as the eighth power of x. A. Not 8, A. I can't say that, I can't differentiate that very well. But so f of x varies as the a power of x. So going back in here, remember direct variation, inverse variation, going back in here and talking about that, or the phrasing f of x is proportional to the a power of x. And so that has to do with that k there. As always, independent variable is x. Remember, x-axis, independent variable, right? And then power functions with positive powers. I just mentioned it, right? Direct variation. So when there is a positive power, that's going to be direct variation. And that's going to fit into the form, if you remember direct variation, remember the form we used? Y equals k times x. Thank you so much. So direct variation, y equals k times x. And as long as there is a positive power here, so a positive a value, it's going to be direct. As opposed to if the power is negative, it's inverse variation. What happens to a variable when the power is negative? Where does that send the variable? To the where? Denominator? If you have a negative power, remember to get rid of a negative power, you move it across the fraction bar and it becomes a positive. Okay, so that's all just some basic information. Okay, so power function, basically x to any power is what we're looking at, and you can have any number multiplied out front. Just forget zeros. So, a couple of small things we're doing. Example 1, we're going to write an equation. Okay? So, from empirical evidence and the laws of physics, it has been found that the period of time t for the full swing of a pendulum varies directly as the square root of the pendulum's length L, provided that the swing is small relative to the length of the pendulum. Lots of information there, right? The directions ask us to express this relationship as a power function. So, a power function of the form f of x equals k times x to the a power. So, my recommendation, let's go back and reread it again, right? From empirical evidence and the laws of physics, it has been found that the period of time t, right there, did you catch that? Period of time t for the full swing of a pendulum, what does it say? Varies directly as the what? Square root of the pendulum's length L, provided that the swing is small relative to the length of the pendulum. So, extra information there. Okay. So notice, the period of time t varies directly as the square root of the length L. Do you remember doing a little bit of this in algebra where we had to write our direct or inverse variation? Since it says varies directly is going to be of the form y equals k times x, except we're not really going to use the, at least I would use the y and x. What does it suggest we use? T, so t varies directly, the square root of L. Thoughts on what we write here? T varies directly.
Y equals T times the square root of L.
Not exactly. I'm not going to use the y at all. Because since it says time varies directly, normally it would say y varies directly, and we'd start with y equals. Since it says time varies directly, I'm going to start with t equals. Okay, and then varies directly, so it's going to be t equals, and then it's k times something, since it varies directly, square root of the length of L. So we can write it as, or at least as a starter step, t equals k times the square root of L. Now, one question though, before I circle that and call that my final answer. Is it to express this as a power function? What form does a power function have? K times x to some power. Do we have a power? No, we don't have a power. You guys remember anything about the square root of L? Because we need the square root of L to be L to some power. What? 1/2? Does that sound familiar to you guys? A square root is written as a power of 1/2. The power on L, which is an invisible 1, is your numerator. The index, which is a square root, so you have an invisible index of 2, is your denominator. That sounds familiar, right? If I jog your memory. So, a little bit better way to write this if we want this as a power function is t equals k times L to the 1/2 is what I would suggest there. And again, that's because they specifically said power function. Power function is k times x to some variable. Questions there? Okay. Let's look at example 2. Example 2, kind of like what we did with polynomials, but state the power and constant variation for the following power functions. My goodness. So, first of all, Remember the form of the power function? The form from up above, I'll write it since I'm scooted down here. F of x equals k times x to the a, where the only restrictions are k and a are non-zero constants. So, as we look at example A, I want to know a power and a constant of variation. And this is f of x equals the cube root of x. Thoughts here? Do we have a power right now? We don't really have a power, do we? How can I rewrite this? Because before I can really answer my questions here, we have to think of this as f of x equals x to some power. X to what power? 1/3. Because you have an invisible power of 1 over the index of 3. So if we're looking at f of x equals x to the 1/3, what is our power? Power is what? 1/3. So I'm going to say, I'll write it out here for this first one, but the power, I'm going to use A to represent the power. A is 1/3. And then we also have to state the constant of variation. So when I talk about the constant of variation, I want to know what K is. What is K in this problem? Invisible 1? It's not shown out there, but we know that if there's no other number out there, there is an invisible 1 out there. Okay. B. G of x equals 2 over x squared. What should you think about with g of x before we get started on stating the power and constant? How could I rewrite that? It's f of x equals k times x to the a. It doesn't say anything about k over x to the a. So how do I get that x to the second out of the denominator? No, I don't want to multiply. I don't want to move anything over to join g of x. I want to keep g of x by itself.
Make it 2 times x to the negative second.
Yeah, how to move powers across the fraction bar, we mess with the negative exponent, right? If it's in the denominator positive, to get it out of the denominator, we bring it to the numerator as a negative. Just like if it was in the numerator as a negative, how do we get rid of a negative exponent? We move it to the denominator. Does that sound a little familiar? So if I keep my 2 here and rewrite this as x to the negative 2. Now, does that change your thinking on what the power and constant might be? I guess it depends on what you were thinking, right? What would you say the power is now? You guys are so quiet this morning. Negative 2. Okay. And what about our k? What is our constant of variation there? 2, the number that has been multiplied by x. So it does matter that you bring that exponent out of the denominator, okay, based on the form. Okay, C, h of x equals negative x to the negative 4/10. Is there any rewrite we need to do on this one? No, it's already in that k equals x to the a form. So I just need to know what a and k are. What is a? Yeah, my power is negative 0.4. What is k? Okay, there's a negative out front, so that means my k is negative 1. So there's a constant of variation of negative 1. And D, m of x equals negative 3. Thoughts on m of x equals negative 3? A equals 1. So if we're saying a equals 1, that means there's a power of 1. What is our power supposed to be on? Let me ask that. X. So if we're going to say power of 1, is that the same? Okay. So it's not a 1 there. If we're going to have that x there, well, I guess I'll erase the whole thing now. Power of 0. What would make that x be non-existent? And that would be a power of 0, yes? So this is, if you want to think about what it, a different way to rewrite it, because we have to talk about the power of x, right? Negative 3, x to the 0. Because anything raised to 0 is 1, and so that's why it wouldn't have to be there. So, now what are your thoughts? A equals 0. K equals negative 3. Check out your definition up above. What was the definition of a power function? Where k and a are non-zero constants. What did you guys just tell me a is? 0. So what? So it's not a power function. Found the trickery one, right? Okay, because a worked out to be 0, this is not a power function. Okay, so power functions, the key is going to be they have to involve an x. If they don't involve an x, that means it's x to the 0 and it's no longer a power function. Okay, so basically, as long as there's an x to some power, we can talk power function. Otherwise, we can't. Okay, kind of get that a grasp on that definition. Okay, power function is it has to be x to some power. It can be any power, but there has to be an x there, so it can't be a 0. Now, I mentioned at the beginning of class, I talked about monomials, right? And a monomial, we had multiple terms added or subtracted, but the powers had to be whole numbers. Well, now we get to talk about a monomial function. And with a monomial function, do you remember what a monomial is according to algebra? A monomial is just one term. Remember, a monomial is one term, a binomial is 2, trinomial is 3, and then after that it's just a polynomial with 4 or 5, however many terms. We don't have specific names. So a monomial, this is specifically just one term. Now, as you look at it, notice it says it gives options here. says it could be f of x equals k, which means it could be no x. It could just be a constant, so x could be 0. Or f of x equals k times x to the n. Here's the keys, guys. K is some constant. That's what we had up above. Here's the big deal. N is a positive integer. The wording we used in the previous lesson was whole number. Okay? So here we're talking only positives, and we're talking whole numbers, no fractions or decimals. So if you want your examples, it's 0, 1, 2, 3, 4, so on and so forth. Okay? So monomial, whole number powers. And it can include 0. Power functions, up at the top of the notes, anything but 0. Okay, one last example. Basically some vocab review here. State the degree, coefficient, and independent variable of the monomial function y equals negative 3x to the 5th. Degree is what? Degree is 5, right? But your degree of a single term are the exponents of the variables. So, single term, degree is 5. What else did we want? Coefficient. What do I mean coefficient? The number before x, which in this case is negative 3. And if we want, I guess I wasn't talking about like we did up above, the degree came from n equals 5. The coefficient is your k value, right? And then independent variable. Independent variable. What's my independent variable? What's my input? And that's going to be the x. Okay. X is always our independent variable. So your answer's there, I guess. Degree is 5. That came from n. That was our power. Coefficient is negative 3. That's the k value out front. Independent variable is x. That's your input. Okay. That's what stands alone. Okay. Questions? I think I got everything. Okay. Your homework that goes with this lesson is page 182, 1 through 22. I didn't realize I was going to get you this much extra time. I say it's 1 through 22, but think about some of the things we did here. You know, some of the stuff is very easy. Now, the more challenging stuff is going to be writing some of the equations. That's going to be the more challenging stuff. So give it a start.